Yeah, do we begin? Do we begin?
Yes, we can.
Hello, everyone. Can you hear us? Yeah, okay. Okay, so hello everyone. I'm Mike, I'm from Coates, and this is Yeed. Yeed is from PlasJam, and we have a presentation today about a thermoplastic composite bracket, okay? Our agenda, we'll introduce ourselves and the companies we work for, the project background, a case study going into the details of the project, a summary, and then the sustainability aspect from it, okay?
So, hello everyone again. I am Yiğit from PlasJam. So, I will just briefly go over who is PlasJam. So, PlasJam is established in 1983 as an automotive supplier. Currently been working on different commodities in automotive business. And PlasJam is doing plastic injection molding, composite processing, and production tools of these both production techniques. So I will give the word to...
Okay, so Coates is a 250-year-old company. We have around $1.5 billion worth of sales, and we have two customer segments. Hopefully, and I'm pretty confident that you are all wearing some of Coates material today from our apparel and footwear thread business. And then we have the performance materials business, and within that we have personal protection, transportation, telecoms, energy, and then obviously composites. Okay.
So we can dive into our project now. So first of all, I would like to tell you about the start of the project. So our project is content is a tunnel bracket. What is tunnel bracket? Is currently tunnel bracket is a two-layer sheet metal component that is mounted beneath the chassis and supports the vehicle when it's subject to side loads. When we say side loads, we are generally talking about Euro and cap side impact loads. And for the performance of this metal brackets, first of all, we have made a CAE analysis and a physical test. According to the CAE analysis, we see we simplified the requirement to a simple compression load, and the targets we are having between the sheet metal tunnel bracket and thermoplastic composite tunnel bracket is like this. We are aiming to achieve 40% weight reduction. Still, we will be achieving keeping the 100% recyclability. Sheet metal version is two parts. Our composite material is mono component, just one part, and compression performance of the sheet metal is 35 kilonewtons. We are aiming to achieve more than this value, and we also need to say that sheet metal version is electro-coated, and thermoplastic version will not be coated. So here we are seeing the physical performance compression testing of the sheet metal tunnel bracket, which the compression load is measured as 35 kilonewtons. And after identifying the requirements of the tunnel bracket, we can talk about what kind of concepts and material selections we can achieve with this composite project. So on the reinforcement side, we can use carbon fibers, continuous glass fibers, continuous hybrid fibers. When we say hybrid fibers, glass fibers can be in it, carbon fibers can be on it, basalt fibers can be in it, and also there can be alternatives for bio-based fibers also. We are aimed to make the composite laminates from tailored fiber placements, which Coates is the expert for this process, which Mike will tell you more about this process on later on slides. And also, for the composite laminate material, we can use polyamides, polypropylene. Of course, there is no limit. More materials can be used, but according to the aim of the project, we choose 2 materials. Then after composite side, we are having a plastic injection molding or over molding. On that side also, again, the materials are not limited to this, but we can use more or less every thermoplastic material which can be injection moldable. So we are here comparing the design of sheet metal version and composite version. On the purple you see a 2-layer steel, which is the existing design. Then we have a blue is the thermoplastic composite, and we add on an overmolding of a plastic injection molding, which is the green color. And I have to say that in the design, to avoid, to withstand the tightening torque of the bolts, we also use metal compression limiters. When we start designing this thermoplastic composite tunnel brackets, we first start with material characterization. We do characterize our material according to MAT 58 material card. Then we do apply CAE analysis to find out we are going in the right direction. And at this side, I will give the word to Mike to talk about more codes.
Yeah, so the actual process that we defined is that we take a reinforcement fiber as coats, and we take a matrix fiber, the thermoplastic, and we commingle it. It's a standard process. However, Coates has developed their process to be less harmful in the commingling, so we believe we produce a better fiber that can be used in the preforming process. So the preforming process we use is termed lattice, and we take all the design inputs from PlasCham from an engineering point of view and design a preform, as an example here, where we can actually put the fiber in a net shape, so there's waste reduction, and we can also put the fiber in any direction that we want, which can then manage the load that is required, so very specific. The process then continues into compression molding, heat and pressure, and then the overmolding process. So, as mentioned, if you can see the images now, the bobbin of Synergex, that's the commingled fiber, and in this case it's carbon fiber with PA6. It can be glass, it can be aramid, it can be PP, it can be PEEK, it can be PPS, it can be PLA, for example. And then the lattice preforming process, as mentioned, this is where we can lay the fiber any direction depending on the load paths. And in this example, the preform was around 15 layers. The actual fiber is laid onto a thermoplastic backing. So if you want to come and see me after, I can show you more detail. But there's a thermoplastic backing here, which is PA6. The fiber is laid down, and then it's stitched with a PA thread. So when it's compression molded, it all consolidates. Okay? And as mentioned, the lattice preform, as you can see in that example, you can see the fiber is in multiple directions, and there are reinforcement structures. Over to you.
And now I will tell you about the process technique of composite consolidation and forming. We do have developed and implemented this molding technique with rock tool, rapid heat and cool cycle molding. So the input of the process is a laminate, which we call the lattice, and in this process we are aiming to consolidate this material and form it in 3D shape, which will result into similar this shape, let's say. In this couple of shots from the tooling, so the PREFORM I show you, it is placed into the mold, then we heat up the mold to approximately 300 degrees Celsius, then hold it for consolidation under pressure, then we cool the tool to 70 degrees Celsius to take it out of the tool. After this operations are done, it will be ready for overmolding. Then we do place this inserts into the tool. Then we do back injection at the back of these parts. So once the parts are finished, now it is ready for validating the performance. We do validate the performance for these materials, and we see results above our targets, which is approximately 46 kilonewtons in average. So the existing sheet metal one was 34 kilonewtons in average, and the composite one is 46 kilonewtons. And when we compare the weights of the component with the sheet metal, we can see of a 45% weight reduction according to sheet metal version. I will have to again say that the performance is higher, and also the weight is lower. So, as a summary, what we have done, we do take a sheet metal component, which is a tunnel bracket. We redesign and redevelop the material according to composites, and we do use Synergex lattice technology, and also on the molding side, we do use rock tool induction heat and cool process. So when we compare the steel part with the thermoplastic composite part, we achieved 45% weight reduction in here. Again, on recyclability side, we have achieved 100% recyclability. The part is monocomponent. As I have shown you the results of the compression load, we have achieved 46 kilonewtons of compression load, which is approximately 20% higher than the sheet metal part, and we don't have any kind of extra coating on the parts. So we would briefly want to talk about the sustainability of the material we are talking about. We said that the parts are all thermoplastic, so we can say that any scrap of the parts, which can be trim scrap during the process, scraps during the process, end-of-line products, everything can be regrind and can be used on molding different components, or even can be used molding the overmolding of the existing part. So we can use the weights in a circular recycling system on the same part, or any other projects can be developed for this. And existingly, we are developing different projects on serial production to use the production waste and end-of-life products to be usable on the other products as well. So this is all for our presentation. We will be handing over these parts to you for you to check, right? Yeah. Then we are here to get your questions.
Yep. Any questions, anyone? We have some parts there, so please put your hands up and ask. No questions?
Yeah, hello. I have a question. So you made the comparison between...
Sorry, we cannot hear you.
You cannot hear me?
Can now.
Now,
Yeah,
okay.
yeah.
So you made the comparison of, let's say, mechanical properties.
Yes.
So when it comes to pricing, can you also do give some indications if you compare the steel part to the alternative material?
Yeah, so we are comparable to steel. No, we're not really. We're not really. We all know that composites are more expensive than steel. We're probably at this moment in time around 4 times as expensive as the metallic part. However, there are opportunities for us to improve the efficiency of, especially if we look at the material selection. So the materials used were 24K, and we know we can use 48K, for example. Deposition rates are improved, etc. And if you think we are pressing one component in this example, you know, if we went into serial production, we would probably be pressing 4 components at the same time. So I think, or I expect that we could probably get to around 3.5 times the metallic. But again, you know, where we are now will be different to where we are in 3 months because of steel is going up in value, carbon's going up in value, etc., etc. But at the moment, we're around 4 times. Okay, and we have, you know, roughly a 50% weight reduction, which is the key. Okay.
Any other questions?
I saw that you selected TFP process as production. So what was the aim of the selecting TFP process? I mean,
Yes.
is like why you are not using fabric or something like that?
Yeah, so there's 2 aspects to the TFP. One is that we can produce near net shape, so a significant reduction in waste. If you think a comparable NCF product would have 25% waste when you're cutting out. So material waste is key. And then the other major benefit is we can put fibre in any direction, so we can manage the load paths specifically. So we're not overcompensating again with a fabric which is in plus minus 0.90s or plus minus 45. So the TFP allows us complete design freedom with fibre paths. And then, you know, an added benefit of that, we are currently, and if you visit the booth that we have lattice preforms and components with recycled carbon and recycled polyamides and also bio-based polyamides. So we are getting to the point now where we can handle discontinuous recycled carbon fibre through our process, which is obviously very difficult in a weaving or an NTF process.
Yes. Mike shortly describe about the flexibility of the TFP process. Mike, Coach side is the producer of the TFP. Plasjam side is the user of the TFP. From the user side of the TFP, you can have the fibers in any direction, any layer. So it gives a very big design freedom to the customer. And also, as Mike said, the waste percentage, trim waste percentage is very less according to any standard organo sheet or any other process which is valid on the market at the moment.
Any other questions? Anybody? Okay. Yeah, well, we did show a cycle time on the actual pressing side. The moulding side of it is around 7 minutes for the moulding. The TFP process is around 4 minutes. The overmoulding is around 60 seconds. So that, you know, the main part of the cycle is the moulding process. And with the rock tool system, we get to around 7 minutes. You know, again, we could probably improve that depending on the tooling we use, etc. But 7 minutes for me is quite impressive for a thermoplastic component.
Yes, as Mike said, the bottleneck is the 7 minutes molding cycle time. At the moment, we are using rock tool system with heat and cold platen system. So this can be improved. The cycle time of the molding can be improved by using steel induction systems, again from rock tool, and also multiple cavity molding is possible to increase the capacity of the product.
Have you studied aging of the port and the UV and moisture and temperature influence?
Sorry.
Yeah, it was right here.
Okay.
Right there.
Okay.
Yeah, right. Have you studied aging of the port under UV and moisture and temperature influence?
Actually, we haven't done a detailed analysis for moisture absorption, but as we know, this is thermoplastic material, and this is polyamide mainly, and we will see that the moisture will affect the performance, of course. But we always test it on the dry condition. With moisture condition, generally the achieved values will be higher. But we all know that in thermoplastic, especially polyamide, the moisture content will change the performance, but according to these results, it won't get worse.
Right.
But if you are asking about the aging of the product, yes, we have done aging testing according to OEM standards, and it passed all the tests.
All right.
We will have to say. So according to exterior trim aging tests, it passed the requirements.
All right. Thank you.
Thank you.
Are we done?
Any other questions? So we would like to thank again to our teams which are here and not here. We have the chance to present this project here, but we have to say that the project is not just created by us. So there is a big team supporting these projects from Coast side and also from PlasJam side. We have a huge team, and we would like to thank all the team in here.
And if you want further information, we are located in Hall 6, stand 49. Okay, I think it's G49. Okay, thank you very much.
Thank you, everyone.